So in this video, we're going to be looking at the sine law. The sine law is really useful when you have oblique triangles. So this is a triangle that does not have a right angle. If you have a right angle triangle, you'll always use SOHCAHTOA and Pythagoras' theorem. So if you have a right angle triangle, you're going to want to use SOHCAHTOA or the Pythagorean theorem. Those are just way easier. Pythagorean theorem. There we go. So those ones are a lot simpler to use. So if you have a right angle, use those ones. But if you have an oblique triangle, so that's a triangle that has no right angle in it, then neither SOHCAHTOA or the Pythagorean theorem apply. You're not allowed to use them. And so that's where you'll need to use something like the sine law. So how it works is we label all the sides of our triangle, A, B, and C. We use lower cases for those just to keep them straight. So lowercase letters will mean sides. And then you want to label the angle that is opposite the side with the same letter but uppercase representing an angle. So if this is side A here, then over here, right opposite that side is angle A. If this is side B here, then opposite that side is angle B. This is side C here, then opposite that is angle C. And our sine law is simply this. So our sine law is that the length of side A divided by sine of angle A is equal to the length of side B over sine of angle B. And you can take the sine law in any part. So you could do that first part, just that much. Or you could do like this second part, you could do this much. Or you could do that A over sine A equals C over sine C. You can use any part of that sine law to solve the problem that you need to solve. So let's try an example here. Let's say you have Ashley, Dylan, and Peter, and they're all playing soccer. So you've got Ashley over here. Maybe Dylan is here, and Peter is here. So they're forming a triangle while they play soccer. The first thing we see is that from Ashley's perspective, it looks to her like Dylan and Peter are separated by 72 degrees. So that means that this angle in here is 72 degrees. That's angle A, standing for Ashley. From Peter's perspective, so that's angle P over here, Ashley and Dylan appear to be separated by 55 degrees. So he sees an angle of 55 degrees in here. We don't know angle D, the angle that Dylan sees, but we do know that Ashley and Dylan, so this side here, so this is side P, lowercase p, are 23 meters apart. I know that that side should be called P, right, because it's opposite angle P. It's opposite of Peter's angle. All right, and what we're trying to solve for is how far apart are Dylan and Peter, so that would be side A here. That's what I'm looking for. All right, so when we set up our sine law in this case would look like this. So we do A divided by sine of angle A will equal P divided by the sine of angle P. I don't need to use Dylan's angle or Dylan's side opposite here because I'm not asked for either of those, so I can skip that part. If I did need to find Dylan's angle, it would be pretty easy. I know that all the angles in a triangle add up to 180, right? So that's how I would solve for that if I needed. But I'm not asked to here, so we won't worry about it. We just want to solve for P, for A, sorry, how far apart Dylan and Peter are. So I need to rearrange this for A. So the easiest way to do that is probably multiply both sides by sine A. And that's going to clear that sine A off the bottom here. So what we'll get is A is equal to side P divided by sine of the angle P multiplied by sine A. And let's just plug in our numbers. Side A will be the 23 meters divided by sine of angle P, which is 55 degrees, and multiplied by sine of 72 degrees. Then you can just plug that all into your calculator. So 23 times sine of 72 divided by sine of 55, and I get 26.7 meters. So that means that Dylan and Peter are 26.7 meters apart. All right, here's where the sine law gets really tricky. So let's say you have a triangle that has side A is 3, side B is 4, and angle A is 30 degrees. The first triangle I might draw when I think about this might look like this. Maybe this is side B here, that's 4. Maybe this here is side A, that's 3. This is side C, I'm not told what C is. And angle A is right in here. Angle A is 30 degrees. This would be angle C, capital C there, and this would be angle B. All right, so that's the triangle that I might draw sort of off the bat. But is there actually more than one triangle that I could draw that would still fit the same description? Well, what you want to think about is there a way I could maybe swing side A here, kind of rotate it and swing it over, and I could kind of swing it over here. It would still fit in there, and see how that A is still equal to 3 centimeters long, or 3 whatever units long, but I've made an entirely different triangle. I'll draw it separately so you can see it better. I'll erase it in there, but I'll draw it on its own. So what I could also draw would look like this. I'd have the same side B equals 4. I'd have the same angle in here of A, that's still 30 degrees, right? That should look the same. But instead of A going this way, I'm going to swing A in, keep it the same length. So A is still 3, but I've made C a lot shorter. That's angle C up here, and I've made angle B obtuse instead of being acute. So those are two completely different triangles that actually both fit this description. One has angle B as an acute angle, a small angle in here. The other has angle B as an obtuse angle. And they both fit the same description. So this is the ambiguous case of the sine law. It comes up anytime you have two sides that you know and one opposite angle. So if you notice in the first question that we did here, with Ashley, Dylan, and Peter, we knew two angles and one side. If you know two angles and one side, that means you automatically know the third angle, right? Angle D here we could get by doing all angles add up to 180 degrees. So I could find angle D by just subtracting the 72 and the 55 from 180, which would be 53 degrees. So I know every single angle. So that triangle is fixed, right? I know that's 53 degrees then in here. And if I know that side, then every side length will be fixed. There's only one answer for A. But if you know two sides and only one angle, well, you can't just easily find an extra angle by doing all angles add up to 180 because you don't know two different angles. And so you're in this weird spot where there's actually two answers. And so we'll get, when we solve this, we'll find out there's one answer for B that comes out of our sine law, but the other answer for B we'll actually have to get using our related angles that we learned about before. So those will come back for an application here. All right, let's try this here. So this is our triangle. Side A is 3. Side B is 4. Angle A in here is 30 degrees. We don't know side C. We don't know angle C. We don't know angle B. First, I'm going to calculate it for this triangle here. So what we do is we set up our sine law, right? Side A divided by sine of A. It's going to be side B over sine of B. In this case, I'm trying to rearrange for something on the bottom. So probably a good idea to rearrange for something on the bottom is cross multiply and divide. So we're going to cross multiply the A times sine B will equal the B times sine A. So sine A times sine B is equal to B times sine A. And that's just handy because it gets rid of the sine B on the bottom. You can't rearrange for something that fits in the denominator. You need it in the numerator. Then we can divide both sides by A, and that'll give me sine B on its own. So let's plug in our numbers here to see what sine B is. Side B was 4, angle A is 30, and side A is 3. So you want to plug that all into your calculator. 4 times sine of 30 divided by 2 is sine b will be equal to 2/3, the fraction 2/3. Right, to solve for b though, the first way we do it is we just do an inverse sine. So this will be like b1, your first angle. b1 is going to be the inverse sine of 2/3. And if I do that, so inverse sine that, I get b1 is 41.81 degrees. And that kind of looks like my picture here, so that's good. It kind of works. This is 41.81 degrees in there. But we know there's a related angle for B, right? The related angle is going to be B2, which is 180 minus B1, or minus the 41.81. So 180 minus that will give me a B2 of 138.19 degrees. So that's my other answer, and that is the answer to this triangle here. Oh, sorry, not that way at all. This way. So keeping the same length of side B is still 4, side A still needs to be 3. This still needs to be 30 degrees for angle A, but angle B here you can see is much bigger, it's obtuse, and that's exactly what we got here. 138.19 degrees is an obtuse angle. Just by the way, if you're ever solving for C, angle C up here, you don't need to do your related angle again. So once you've found two angles in a triangle, you'll always just solve for the last one by doing all angles in a triangle add up to 180. So you'll do, for C here, I do 180 minus 30 minus the 138.19 that I found. So angle C would be 11.81 degrees here. In this angle, see here, same idea. I would do 180 minus the other angles in that triangle, 30 minus 41.81. So you'll see, so there's no more related angles. You just do the related angles when you're doing an inverse sine, right? So we don't do them again later on, or you'll get weird numbers if you do it twice. So that would be 108.19 degrees. Right in there. And you can see it kind of looks like around 108, and this one kind of looks like around 11.18. So it fits with what our picture looks like as well. All right, so to wrap that up, there are basically two times that you will use the sine law. First, we only use it with an oblique triangle. If you have a right angle triangle, just use SOHCAHTOA and the Pythagoras theorem. They're just way easier. You can actually use sine law on a right angle triangle. It's just there's no point. It's more work. And there's two times you'll do it. If you have two angles that you know, and then one opposite side. So see how this side is opposite an angle that you know? That's an example of where you will use the sine law. Or if you have two sides and one opposite angle, so that angle is opposite a side that I know here, I'll also use the sine law there. But in this case, where you have two sides and only one angle, this is where you need to worry about the ambiguous case. So just in the case of where you have only one angle and two sides, where one of them is that opposite side, that's where you have to do an ambiguous case. If you have two angles, there's no ambiguous case there. You're good to go.